to the next chapter 14. So we'll just spend the last little bit just getting into chapter 14. Okay, we did Charles' law and Boyle's law. There's another law called Avogadro's law, and this is for gases. And that is the volume is proportional to the number of gas particles that we have in there. That's Avogadro's law. The number of gas particles is going to be given by the moles. So this is Avogadro's law in action here. So if we look at O2 and H2 reacting to form H2O, but we know the stoichiometry of the reaction. The stoichiometry of the reaction is like this. It's going to be O2 plus 2H2 yields 2 H2Os. Okay, we're going to do all this in gas. So this will be gas, this will be gas, this will be gas. Avogadro's law just says this. If I take 1 liter of oxygen gas, I'm going to need 2 liters of hydrogen gas because 2 liters will have twice as many particles. And that's going to give me 2 liters of H2O gas. All these have to be gases for this to work. And so 1 plus 2 liters is going to give me 2 liters here. 1 liter of oxygen plus 2 liters of hydrogen gives me 2 liters of water. And so this is the law of combining volumes. Combining.
Why isn't it 3 liters?
Why isn't it 3 liters? If it were just a mixture, if we're mixing like a physical mixture, but it's a chemical reaction, so the atoms are rearranging. The number of particles are changing. So we're going
Does it
from...
happen even if there was nowhere for the other gas to escape?
Well, other gas, these 2 gases are being destroyed. These 2 gases are being destroyed. The bonds are being broken in the gases, and the new bonds are being formed. And so we no longer have these gases here. If the gases weren't, if we just had a physical mixture, let's say we mixed oxygen and hydrogen, then we'd have 3 liters. But what's happening is a chemical reaction is happening. If there was no chemical reaction, we'd have 3 liters. Since there's a chemical reaction occurring, we're only going to end up with 2 liters. 2 liters because of the stoichiometry of the reaction. Yeah, you got to think about it for a bit, but we'll do more examples here. If you have 50 milliliters of O2, you'll need twice as many hydrogen particles. So it's 50 milliliters, 100 milliliters, you're going to form 100 milliliters. So 50 milliliters plus 100 milliliters gives you 100 milliliters of O2. That's the same thing. Think of it this way. How about this? How many total moles of gas do we have at the beginning? Well, we have 1 mole of oxygen, 2 moles of hydrogen. How many moles is that altogether? 3. Shouldn't we have 3 moles at the end? Should we have 3 moles at the end? No, because this is chemical reaction occurring. Chemical reaction is occurring, giving us. If this were just a mixture, then we'd have 3 moles, but it's a chemical reaction, so we don't necessarily have 3 moles. Going to have whatever moles that we're given. And since the moles and number of particles are related by Avogadro's, we'll see. And so here it looks like what they're doing is they're going from here, they're doubling. If they double the number of particles, they're going to double the volume. And so here it looks like they're tripling. So if they triple the number of particles, they're going to triple the volume. So the volume is directly proportional to the number of particles. The number of particles is directly proportional to the number of moles. And so these equations here can be mole ratios and volume ratios. They can be volume ratios as long as we constrain things. We got to constrain it to constant pressure and constant temperature. And then, yeah. And so what we end up with is the 3 laws. Charles' law, volume is directly proportional to temperature. Boyle's law, volume is inversely proportional to pressure. And Avogadro's law, volume is directly proportional to the number of moles or the number of particles. And so if we combine all 3 of these, we get the ideal gas equation. The ideal gas equation is going to look very similar to the combined gas law. The combined gas law was P1 V1 over T1 is equal to P2 V2 over T2, which is equal to constant. Okay, all we're doing is we're adding Avogadros. When we add Avogadros, it's the moles as well. So P1 V1 over N1 T1 is equal to P2 V2 over N2 T2, which is equal to the constant. This constant we're going to give a name to this time. The constant is going to be called R. R is equal to the gas constant. And so, simplifying this equation, we have another form for this equation, and that's PV equals nRT. This one is called the ideal gas law. Ideal gas law. This comes from empirical equations. So all we do is we memorize these two equations. We memorize these two equations and basically do calculations based on the law, the empirical equation. And so what types of calculations do we do? Well, one is ideal gas law came from Boyle's law, Charles' law, Avogadro's law. So all the Boyle's law problems, all the Charles' law problems, and all the Avogadro's law problems, which we haven't done yet, will be doable using the ideal gas law. So we only need one law for all of this. So what we can do is we can just eliminate. So Boyle's law, we no longer care about. Charles' law and Avogadro. We have a much more versatile law. And so this is why, yeah, so okay, you might have remembered the names, but now you're going to forget the names because we're never going to go back and use these, basically. Because we can do all gas problems using just these two equations here. In fact, just one equation, because this equation can be simplified to this equation quite easily. And so the examples of using this are just algebra. A 0.1000 mole sample of helium is placed in a piston and heated to 25 degrees C. The volume is adjusted to 4.600 liters and the resulting pressure is measured as 0.5319 atmospheres. Use these data to determine the value of the universal gas constant. And so, when we have a gas, we want to characterize these things: the pressure, the volume, the number of moles, and the temperature. These four characteristics we need to determine. And so the pressure is going to be 0.5319 atmospheres. That here, 5319 atmospheres. The volume, 4.600 liters. The number of moles, 0.1000 moles. Temperature is 298.15 Kelvin.
So this is always in Kelvin?
Yeah, you always need it in Kelvin for any gas problem. And so what we're going to do is N is always moles. Yeah. And so R is just going to equal to solving this PV over NT, PV over NT. And so pressure, we'll just plug it in here, 0.5319 atmosphere. Volume, 4.600 liters, divided by N, 0.1000 moles, and T, 298.15 Kelvin. So this should give us 4 sig figs. Let's take a look at what it comes out to. 0.5319 times 4.6 divided by 0.1 divided by 298.15. Zero 0.08206.4 Okay, I'm gonna rearrange the units. I'm gonna call liters times atmosphere over mole Kelvin. So what people do is they memorize this. You should too. You memorize R equals 0.08206 liters atmosphere per mole Kelvin. It's not just one data. If we just did one data point, that is, if we just did one experiment, this experiment could be in error, huge error. But what people have done is they've done many, many experiments and then averaged it. And then this is the number that you come out with, R. In fact, let's take a look at what R is on Wikipedia and see, or some other source.
What does the universal gas constant mean? What is that?
What it is these, basically these laws come from what? They come from experiment. And so people do this experiment and they always see that they come up with the same ratio. PV over NT comes out to the same ratio. And so just empirically, it comes out to this number here. And so over a large number of experiments, this is the number they get. 0.082057338.
Well, like, what does that measure? So is that like, okay, if I increase the degree by 1, my liters per atmosphere is going to increase by 0.08206? Like, what does that measure? I don't understand what R signifies.
What it doesn't measure anything. It's just a constant. So the way you look at it is this. Let's say if the numerator increased by 1, the denominator has to increase by 1, whether it's, you know, n or t or whatever it is. And so if the numerator gets cut in half, the denominator has to get cut in half. It's because this has got to equal this constant. That's it. And so if everything's set, and then if everything's set, then we should get this constant. So this is why we get this. The first equation I wrote there on the board. The first equation is this: P1 V1 over N1 T1 is equal to P2 V2 over N2 T2. Do you see R in there? 0.082. Is there any R? There's no R there. It's just if we increase this ratio, then we got to increase that ratio. This ratio is just got to be equal to constant. And so whatever we do to the numerator can be done to the denominator too. And so if we start tweaking some of these numbers and playing around with them, then it's going to change it. It's no longer going to equal R. It's going to equal R. And so the first type of calculations we do are just these type of calculations. The first type of calculation we're doing here is we're just, well, first we determined what R is here.
R is always the same number.
Yeah.
No matter what.
Right, it's always the same number, so therefore we can calculate the missing data. And so we get the R value here. We got the R, 0.08206 atmospheres liters per mole Kelvin. Now what can we do? Okay, let's take a look at the types of calculations we do. So I asked you to memorize R. Once we memorize R and the ideal gas law, then we do this, determination of a single variable. And so a typical calculation would be just to determine a single variable. This is actually 2 different slides on one, but let's see if they have a single variable here. A single variable would be something like this. What is the pressure in atmospheres in a helium-filled 0.77 liter balloon if it contains 1.0 grams of gas at 22 degrees C? So we have a gas, and the gas can be characterized by 4 things. The 4 things that can characterize a gas are going to be pressure, volume, amount, and temperature. And all these are related by R. And so here we're gonna have helium. We got 1.0 grams of gas. The temperature is 22 degrees C, and the volume is 0.77 liters. And so we'll put it in here, but we don't know what the pressure is, so the pressure is unknown. The volume's known, volume's 0.77 liters. The amount is known, but the amount is known in grams, so we go from 1.0 grams of helium, and then we're gonna convert that to moles. A mole of helium weighs how much? A mole of helium weighs 4.002 grams of helium. And so the grams of helium cancel, and that gives us about a quarter mole of helium. And then we can do the temperature. The temperature is 22 degrees C, which is equal to, well, 273. That would be equal to 295 Kelvin. And so what we can do is we can use it to solve for pressure. The pressure using the ideal gas law is equal to nRT over V, just rearranging that equation. And so N is this. I don't know how many moles did that come out to. 1 divided by 4.02. 0.249 moles of helium. So what we'll do is we'll go 0.0249 moles of helium times R. We memorize this R. It's going to be 0.08206 liters times atmosphere per mole Kelvin times T, 295 Kelvin. 295 Kelvin divided by V. The volume is 0.77 liters. And so when we look at this, the moles of helium cancel moles, liters cancel liters, Kelvin cancels Kelvin. That leaves us with atmosphere. And so we can use this to characterize the gas. Okay, that's it for today. We'll continue tomorrow.